So, a theory of everything, it's a pretty big idea, right? Trying to find one equation that explains, well, the entire universe. It can be a lot to wrap your head around.
It's definitely ambitious.
Hmm.
But what's amazing to me is how far back this idea goes. It's like we're wired to look for patterns and connections to find that underlying unity in everything around us.
It's true. When you put it that way, it's not such a giant leap from, say, ancient philosophers thinking about atoms to modern physicists grappling with string theory.
Exactly. It's a continuous search for knowledge.
And speaking of string theory, I think it's time we define what we're actually talking about when we say theory of everything. It sounds kind of like a science fiction concept, doesn't it?
It does, a little bit. But in physics, a theory of everything, often shortened to TOE, kind of catchy, right, aims to be the ultimate explanation of, well, everything. Think of it like the universe's instruction manual. This single set of rules could, in theory, explain everything from the tiniest particles to the largest structures in the universe.
It's almost a dizzying thought trying to grasp the entirety of the universe with a single theory. Where do you even begin to look for something like that?
Well, you have to start with what we already know. And in physics, that means looking at our two most successful theories, general relativity and quantum mechanics. The challenge is, these two theories, while incredibly good at explaining their respective domains, don't really play well together. The theory of everything has to find a way to unify them.
So it's like we've got two pieces of a puzzle, and they should fit together, but something's not quite right.
A very good analogy. We have general relativity, which is fantastic at explaining gravity and the large-scale structure of the universe. Think planets, orbiting stars, galaxies colliding, that sort of thing. And then we have quantum mechanics, which governs the world of atoms and subatomic particles, a world that often seems very strange and counterintuitive.
Okay, so on one hand, you have the massive cosmic dance of planets and stars and galaxies. And then on the other, you have the almost invisible world of quantum particles, where things aren't always so clear-cut. Where does the conflict arise?
The problems, or I guess you could say the really interesting parts, happen when you try to apply both theories to the same situation. Think about the singularity at the heart of a black hole, for instance, or the very, very beginning of the universe. These are moments where gravity is extremely strong at incredibly tiny scales. Our current understanding, our current theories, simply break down at those extremes.
I just can't explain it, huh? So where do we go from there? Did anyone, say Einstein, ever try to find this missing link?
He did. In fact, Einstein spent a good chunk of his later years searching for what he called a unified field theory. His idea was to weave together gravity and electromagnetism, which were the only two fundamental forces known at the time. Unfortunately, he wasn't successful.
I see. So it's not for lack of trying. Was it just a matter of, like, the math being too complicated, or were there deeper issues?
It was definitely a combination of factors. For one thing, we've learned a lot since Einstein's time. We now know about two additional fundamental forces, the strong and weak nuclear forces, which add a whole new layer of complexity to the problem.
Ah, so even if he had managed to unify gravity and electromagnetism, there were more pieces to the puzzle waiting to be discovered.
Exactly. And on top of that, the development of quantum mechanics, with its probabilistic view of the universe, presented a fundamental challenge to Einstein's own view, which was much more deterministic. He famously said, "God does not play dice."
Hmm.
He had a hard time reconciling the randomness inherent in quantum mechanics with his own ideas about a universe governed by predictable laws.
It's fascinating how the pursuit of a unified theory often uncovers even more mysteries.
It's true. And that brings us to the Standard Model of particle physics. Now, while not a theory of everything, the Standard Model does a pretty impressive job of unifying three out of those four fundamental forces we've been talking about.
The Standard Model. It feels like we're getting closer, right? But I know there's more to the story. It's not quite the whole picture, is it?
You're right, it's not the whole picture. The Standard Model is a remarkable achievement, it really is.
Yeah.
But it's like we've put together this beautiful puzzle, and then we realize there are these pieces missing, important pieces, and the model, it just doesn't have a place for them.
You're talking about dark matter, dark energy, those kinds of things, the big cosmic mysteries.
Exactly. Dark matter, the invisible stuff that's thought to hold galaxies together, and dark energy, the mysterious force that's pushing the universe apart, making it expand faster and faster. The Standard Model, for all its successes, it just doesn't address these mysteries at all. It's silent on them.
Which is pretty frustrating when you consider how much of the universe seems to be made of this stuff we don't understand. It's like we're missing the key ingredients to the cosmic recipe.
And that's where things start to get really interesting, I think.
Hmm.
Because to tackle these bigger mysteries, these missing pieces, we have to start considering some really radical ideas. We have to go beyond the standard model.
We're talking string theory. That's where things start to sound a little less like a textbook and a little more like science fiction.
Well, string theory definitely captures the imagination. It starts with this bold idea. What if, and this is really at the very heart of it, what if the universe isn't made of tiny point-like particles? What if, instead, everything is made of tiny vibrating strings?
I've always liked that image. It's like the universe is a giant symphony, and all the particles and forces, they're just different vibrations of these cosmic strings. Beautiful, but hard to wrap your head around. How do you even begin to picture something like that?
It is abstract, no doubt about it. It takes some getting used to. Think of a guitar string. When you pluck it, it vibrates at a certain frequency, and that creates a specific note. String theory proposes something similar, but on a much, much smaller scale. It says that different vibrations of these fundamental strings, these incredibly tiny strings, they create all the different particles and forces that we observe.
Okay, I'm starting to follow the string part, but then there's the whole idea of extra dimensions in string theory. Are we talking about parallel universes here? Different realities existing alongside our own? Because that's a whole other level of mind bending.
It's not quite parallel universes, but it is mind-bending, I'll grant you that. To make the math work, string theory requires that there are more dimensions than the ones we can see and experience. We experience three spatial dimensions, right? Up and down, left and right, forward and backward. And then, of course, we have time. But string theory says that there are more spatial dimensions, curled up at such tiny scales that we can't perceive them directly.
So we're like fish in a pond, completely unaware of the vast sky above. Or I don't know, maybe a better analogy is an ant crawling on a piece of string. We can only experience the dimension of the string itself, not the dimensions beyond it.
It's a good analogy. We're trapped on our little slice of reality, unaware of these extra dimensions that might be curled up all around us. And here's where it gets really interesting. From a physics perspective, at least, some physicists believe that gravity might leak into these extra dimensions. That could be why it seems so weak compared to the other fundamental forces.
So gravity is weaker, not because it's inherently weaker, but because it's spread out over more dimensions than the other forces have access to.
That's the idea. It's like gravity is playing on a much bigger board. And that has some pretty profound implications for how we understand the universe. But here's the catch. If these extra dimensions are so small, so curled up, how could we ever hope to observe them? How do we prove or disprove string theory if it's based on things we can't even see?
It's like trying to study the fine print on a contract written in invisible ink. But we're not giving up yet. We'll be back right after this short break to talk about the string theory landscape and what it might mean for our understanding of the universe.
I'm ready when you are.
All right, we're back. And I have to admit, my brain's feeling a little bit full of extra dimensions right now. But we were about to dive into something called the string theory landscape. It sounds pretty epic. What exactly is this landscape and why is it important?
Well, it's definitely one of the more, let's say, controversial aspects of string theory. It all comes down to those extra dimensions we were talking about. It turns out there are a lot of different ways those extra dimensions can be compactified or curled up.
Okay, so instead of just having one way to arrange those extra dimensions, string theory says there could be many, many different configurations.
Many is an understatement. We're talking a mind-bogglingly large number of possible configurations. And each different configuration, it would give rise to a universe with its own unique set of physical laws and constants.
So like our universe with its specific laws of physics, the ones that allow for, stars and planets and life as we know it, ours could just be one tiny island in this vast sea of possible universes.
That's one way to think about it. This idea is what we call the string theory landscape. Each point on this landscape represents a different possible universe, a different set of solutions to the equations of string theory.
It's like suddenly zooming out on the map of reality and realizing there's not just one continent, but a whole planet full of them, each with its own unique ecosystem. A multiverse of possibilities.
Exactly. And it raises some really big questions, like if there are all these possible universes out there, why do we live in this particular one? Are there other versions of ourselves out there in other universes? It starts to get pretty philosophical pretty quickly.
A little bit mind-blowing too. But before we disappear down that rabbit hole, we should probably touch on some of the other contenders in this race to a theory of everything. What about loop quantum gravity? How does it approach this challenge of uniting general relativity and quantum mechanics?
All right, so loop quantum gravity, it takes a completely different route than string theory. It's like if string theory is all about looking at the smallest possible pieces of the universe, the strings, loop quantum gravity, is all about looking at the fabric of space-time itself.
Space-time, the very stage on which the cosmic drama unfolds. What does loop quantum gravity have to say about it?
It says that space-time, at its most fundamental level, is not smooth and continuous like we usually picture it. Instead, it's granular, made up of these tiny, indivisible chunks, kind of like pixels on a computer screen.
So instead of a smooth sheet, it's more like a chainmail woven from these tiny loops, these quanta of space-time.
Exactly. And it's at this incredibly tiny level, the Planck scale, we're talking 10 to the power of negative 35 meters, that gravity and quantum mechanics, they might finally find a way to coexist.
So while string theory adds extra dimensions to the equation, loop quantum gravity focuses on the quantum nature of space-time itself. Two radically different approaches to the same fundamental problem.
That's what makes this whole search for a theory of everything so fascinating. It's like we're trying to put together a puzzle, and we have these two completely different boxes of pieces. Which box has the right pieces? Or maybe we need both,
Or maybe there's a third box out there that we haven't even found yet.
perhaps. But even with these two incredibly compelling theories, string theory and loop quantum gravity, there's still this big question. Can we even find a single theory of everything?
Is it even possible?
Some physicists, they'll tell you that the search itself might be misguided, that the universe might just be inherently messy, too complex to be captured by a single theory. Or, here's another thought, maybe our human minds, bound by language and logic, maybe we're simply not equipped to grasp the true nature of reality, even if such a theory does exist.
It's a humbling thought, isn't it? That maybe there are limits to what we can know, even with all our scientific tools and theories.
It is. But even if we never find this ultimate theory, this theory of everything, the search itself is incredibly valuable. Just think about all the incredible discoveries we've made along the way, just by asking these questions, by pushing the boundaries of what we know.
It's like climbing a mountain. Even if you don't reach the summit, the journey itself is full of breathtaking views and incredible challenges. And who knows, maybe the view from the top wouldn't be as interesting if we hadn't taken the time to appreciate the journey along the way.
I think that's a great way to put it. The pursuit of knowledge, it's about the journey as much as the destination.
Absolutely. It's about the joy of exploration, the thrill of discovery, the constant questioning and pushing the limits of what we think we know. That's what this deep dive has been all about. Exploring these mind-blowing ideas, these attempts to understand the universe at its most fundamental level. And while we might not have walked away with all the answers, I think we've gained a deeper appreciation for the questions themselves. And that, to me, is what makes this whole endeavor so worthwhile. So until next time, keep exploring, keep questioning, and keep looking for those connections that bind the universe together.